Okay. Okay, thank you very much. Can we increase? I mean,
oh, let's see.
I have to make it larger on the okay, anyhow, okay. Okay, yeah.
Is it okay? All right,
Yeah,
sorry.
okay, yeah.
All right.
Okay, so yeah, I'm also a little bit perplexed to be in this role. So anyhow, I'll do my best to explain to Rocco and to Joe what are the current computations in lepton scattering. So okay, these are goals of this short presentation. So I mean, it's not going to be a kind of I would call political correct resumes that there will be slides from each presentation from the first week, but well, I'll focus on the topics which are most warmly discussed during first week, and also my perspective will be, I mean, rather practical. I mean, because as a user, rather to focus what is relevant for development of Monte Carlo simulation tools. And okay, and perhaps everybody is tired, so probably there will be no more discussions. But in fact, those who were here can only agree with me that when the atmosphere was, I mean, there were many discussions on and I'm not sure whether we Okay. Okay, so in the center of most of talks of the first week were nucleon-nucleon correlations. So we know they are there from electron scattering, and they are quite important. So there's 20% probability if we pick out a random nucleon that it is correlated, that there is another correlated partner. And okay, spectral function. And actually, we know how to account for that in impulse approximation, one-body current computations, by using spectral function. So this is one of possible schematic visualization of what spectral function is. So here's removal energy. So okay, there is a correlation between nucleon momenta and removal energy. And there's it is a very simple explanation from the presentation by Inge Sieg. Why it is so? Because it costs typically more energy to pick up at once two nucleons out of nuclei. And I mean, the most spectacular manifestation of that, everybody knows, is very simple, very intuitive, is an impact on distribution of nucleon momenta. In the case of Fermi gas, it is just a step function. In the case of spectral function, so in nature, there is a long high momentum tail. Well, if this were the whole story, I mean, the life would be easy from practical point of view, because spectral functions can be easily or relatively easily implemented in Monte Carlos. So there have been a lot of work within Nouvre, more recent work for Gini and Newt. It's pretty much straightforward. Then several spectral functions for targets like carbon or oxygen are available. Moreover, I mean, there are rather clear recipes how, say, to cook spectral functions for remaining nuclei. And it is because this correlated contribution is rather universal. It is always like deuteron-like. So we see these results from some theoretical computations of the momentum distribution, and we see that, I mean, the shape of this tail is always pretty much similar. But it is not the whole story, because correlations also seem to play a very important role in two-body current contribution, which has become in the center of interest of neutrino community during last, I don't know, 3-4 years, maybe more. And here are two tables from the I don't know, presentation or paper by people who are present here. So two-body current contributes mostly, or I mean, to transverse responses. These are electron scattering computations for light nuclei. Okay, and I mean the language is a little bit technical, but after all, I mean the message is that transverse response is enhanced by 30-40%. I mean, depends on momentum transfer, depends on nuclei. So these are full computations. I mean, and on the right-hand side, I mean, we see how important correlations are, because here are, I mean, similar computations with Fermi gas nucleus ground state. Okay, and we see that, I mean, for longitudinal, I mean, this enhancement was already small in full computations, but for transverse, I mean, if we compare, I mean, here is difference. This is for, I don't know, remember which nuclei it is, lithium or whatever. I mean, the effect disappears. So correlations are crucial for this contribution. Now we switch a little bit. We will come back to those computations. These are this is the status of existing computations in which neutrino community tries to accommodate in the simulation tools. So this nice slide is taken from Marco Martini presentation, and we see, I mean, this is simplified double differential cross section. So this is the, I mean, the quantity which various models provide. A little bit simplified because it is assumed here that lepton mass is vanishing here. And we see various, I mean, they are, I mean, this scheme, there are 4 responses, and various models contributes to, I mean, in a different way to them. So in red, this is Marco model, so it gives, I mean, two-body two-current contribution to these 3. Then blue, I mean, Nieves, unfortunately, is not here, but it contributes to all of them. Okay. Then there is superscaling, the superscaling approach in green. So gives enhancements only to GM square, only to this, I mean, this part, not to the axial one. And I added also here transverse enhancement model by Aribodek, which the contribution comes to GM containing terms, so it is a little bit different. I mean, there's contribution also to the axial vector interference term. Then, okay, so they are different. There are different predictions. I mean, different, in particular, some differences in predictions for the effect for neutrinos, antineutrinos. And in particular, one point was discussed many times, namely, I mean, this term, whether there is an enhancement both for say for magnetic square and axial term or not, or okay. I understand this. I learned. I didn't find any figure or table for that, but I learned from coffee break conservation that I mean, that axial part is enhanced as well. Okay.
So what's the conclusion? Yes, it is.
Yeah, it is. So it is. So okay. So we can some models. So if the model, okay. so it is not what is claimed by this model. Okay. Okay, we'll come back maybe to something similar. Okay, then we come back for a second to say to rigorous computations for neutrinos, and they are, I mean, very nice results for neutrino for neutron target, both charge current and neutral current. I mean, these are, I mean, not that new. I mean, they were published a year ago or so. And the result is that, okay, there is, I mean, it is not that small as you might think, because it is logarithmic scale. So effect is, I don't know, 5-6% or so, but still it's not large. Then there is also here explicitly, there is some effect for the axial contribution. Okay, so I think these are really good news, because what we know about MA, I mean, from neutrino experiment, comes from neutron experiments. Okay, it means that, I mean, the values of MA which were inferred from those computations, I mean, can be trusted. I mean, up to 5-6% maybe. I mean, I have also a feeling that it would be nice to, I mean, to see the impact of those, say, rigorous computations on the shape of Q square, because it is how most often experimentalists deduce the number of MA on the shape. So even if, I mean, the overall cross section maybe is not much change, maybe there is some structure, maybe there is some modification of the Q square distribution. I think this would be interesting for experimentalists. Okay, then still, I mean, those rigorous computations, as I call them, there is some progress. Namely, they are computations for carbon, neutral currents. It is not, I mean, what we most are waiting for. Again, in language of some rules. And here it is a nice decomposition of 5. There are 5 response functions, so there are 5 some rules, and I mean, we can, I mean, contemplate them a little bit. I mean, this is the way in which they are translated into another language, which was discussed by Jose Amaro. So those responses, okay, they are, I mean, it is in a frame in which momentum is transferred along the axis. So this is a language used by some other paper. And as far as, and then, I mean, this one is interesting, because in S00 there is no enhancement. And as far as I can, then maybe you correct me, it is this. Yeah? I think it is charge. Yeah. So it is exactly in agreement with Marco-Martini model. There is no effect on this response function, and I find it very interesting.
But because I don't quantify the effect in the near, just to affirm that there is a contribution in the case of Nieves, I don't know.
Yeah. But maybe it is small. Yeah. But in your approach there is no. It is yeah. It's very bad that Juan Nieves is not here too. Okay. I mean, what can be a little bit worrying is that, I mean, it is what I told you, that, I mean, in the case of Fermi gas or local Fermi gas, in these rigorous computations, effect disappears. Okay. While, I mean, those computations, microscopic computations, which are at our disposal, Nieves and Marco, I mean, the starting point is Fermi gas or local Fermi gas. So this is a little bit puzzling. However, I mean, Marco and Nieves computations include contribution from so-called correlation diagrams. Okay, so these such type of diagrams in which, okay, some correlation is put to the system, and I mean, the question is, I mean, what is, which I cannot answer. I I would be interesting to know. I mean, what is the relation between this correlation and correlations which are there in computations we have discussed before. So, in other words, I mean, to what degree this picture which we are obtaining is consistent? Yeah, because I am. It is what. This is another slide from the Marco presentation. I mean, NN is this correlation contribution from correlation diagrams, which I showed on the previous slide, and delta is correlation delta interference. And if we look for, this is a differential cross-section in the fixed value of neutrino energy, 700 MeV, and we see that, I mean, this contribution and that one, they account for probably 75% of the two-body current enhancement. Yeah, there's, I mean, delta delta is, I mean, green and yeah, they are, yeah. Okay, so it is, I mean, that much as.
I don't know if it makes much sense to discuss that single diagram, which by itself is not going to be a gauge invariant for the vector part or filling PCAC for it's going to be representation in so it's going to depend on your representation you use for the field. So that diagram alone by itself is probably not
Okay.
20 years at least, direct translate.
Okay, yeah, I hope, I mean, this point will raise some discussion. So,
that by itself is not gauge invariant, right?
Which diagram are you talking?
The one that was shown by
I mean, this one.
This one.
This one.
I don't know what that diagram is. I mean,
it's two nucleons, an external current, and a pion exchange. I think. I hope that's what it is.
I don't know.
I mean, is there pion or maybe some other bosons? I don't know how it is in your model.
That certainly doesn't
Some
look like a two-body current.
Yeah.
That one normally computes, right? That's not a two-body current the way I
Yeah.
see it. I don't know
Okay.
how you guys computed that.
Yeah, but yeah.
Seems like you have an interaction between three particles and then an absorption of this visual. So that's not the two-body current.
I don't know. Up to you whether we stop at this point or we'll. Yeah, because I also I would like to to know how. Okay, so another point. I mean, next point is for a moment. So we are waiting. Users are waiting for complete two-body current computations on carbon, at least. And in the meantime, we must rely somehow on existing models parameterization. And there are some issues, namely consistency. It is because in all the Monte Carlo, also in Jibu, two-body contribution is added in the, I would say, incoherent way. Is just as another cross-section on the top of CCQE, RES, DIS, coherent, perhaps. However, we also know, or it is a result of the computation, that there is a big interference between two-body and one-body part. So, so first thing is that in Monte Carlo, one needs parameterization of both two-body current and interference contributions together, which probably, this can be done. On the other hand, I started from that. In the impulse approximation and interactive approach is to use spectral function. And in the spectral function, there is some explicit small correlation contribution. Okay, so there are some events in which two nucleons are knocked out, because if interaction occurs on a correlated nucleon, there is another nucleon, a spectator, which also should be thought to be knocked out. So there is some overlap, and the question is how dangerous it is, so how wrong it is, how inconsistent it is to use, for example, this spectral function computations together with, say, Marco-Martini or Nieves models. Other topics. So, yeah.
Maybe elementary question, that part about interference. I've always been a little confused by that, because if those final states with two nucleons are different, there at least won't be complete interference, right? There'll be an extra piece of the cross-section after interference, and so you wouldn't, like in the
yeah, it's not interference between, it's interference within the same final state of different processes.
Yeah.
Okay.
So we can have.
Well, it's not guaranteed that, so both of these things are giving you both one nucleon knockdown and two nucleon knockdown.
Yeah.
Yeah, this is an inclusive calculation. It's very different. What comes out in the actual final states, as far as the nucleon goes, is different. This is for the inclusive cross section. We find a significant interference. It has to be with the same final state between one body currents and two body currents. It's just a high momentum transfer. You can have the momentum coming from the external line, or you can have the momentum coming from the current, and they can interfere.
But if you had a calculation of the one particle knockout and the two particle knockout, you would have interferences within them, but then you can add the two of them together.
Yeah,
Mm.
sure.
I think that's the right way to think about it. And you gotta worry about how the different elements enter
But that
those.
calculation.
And that's all,
Yeah.
but you're not doing that yet.
No, yeah, and it's extremely hard, particularly for argon.
Yeah. Okay. For argon is yeah. Let us.
Carbon, right?
Yeah.
That's why we calculate inclusive cross sections. I know you guys want a lot more.
Okay.
It's very useful, but there's a certain simplicity to the inclusive cross section which is absent.
Joe, can I repeat that? Did I hear you say that in the inclusive calculation, there is interference between the one body and the two body currents? Yes.
That doesn't mean there's interference between one nucleon and two nucleon. There can
No,
be
of
that.
course, yeah, that's different.
Well, so then I was thinking about, does that mean if you're doing different experiments, you would get different, you would get different, anyway, it's too late, I'm just.
Yeah. Unfortunately, it is very late. Everybody's tired.
An experiment whether you see final state or not. I guess what I'm saying. If you're not seeing anything, is that sort of destroying the interference that you would have on the electronic side? Right, think about it just in terms of pure sort of
I mean,
basic quantum mechanics.
obviously the total cross section has to be the sum of the one nucleon knockout and the two nucleon knockout, but in our calculations in particular, the one and two body currents are not directly corresponding to that, right? And that, to some degree, even in the RPA approaches, what's really going on is much more complicated, right? And anybody can do a much better job on the inclusive one. That's what you've seen from all the comparisons in electron scattering, where typically things are much worse when you go to, unless you go to very special kinematics.
Okay, so there was, yes, okay, Jose is here. I thought that all these superscaling people left already, but so there were several talks on say scaling, various type of scaling approach and models, and in particular I've picked out this one, which is very interesting, nice. I mean, this is longitudinal. I mean, longitudinal, say, phenomenological fit to the existing data. And this, interesting that this curve is very much, I mean, it has some shape and is very universal, and provides a simple test for the model, which we can be trying to use. So, for example, we can see how big, how bad the relativistic Fermi gas is when we compare computation results. Okay, so there were various models were discussed. I mean, some of them agree better, some agree worse. However, I mean, since we are, in many computations, and the model for CCQE is the choice is local Fermi gas plus RPA. That would be interesting to see. I mean, which is prediction for longitudinal response for this model. I haven't never seen it. Probably it is, I don't know. Yeah. So other topics. I think this is probably the last slide. I mean, pion production, it is a kind of transition region topic because there was some presentation in the first week, most of them in this week. And I'm going only to show, this slide, this type of comparison was shown many times. It shows how poor is the performance of the Rhine-Siegen model, which is a common tool to simulate pion production in neutrino generators with nature. Here it is in the case of electron scattering. So we have the data, they are very nice data, precise data, and in dashed line is prediction. So for vector part of the Rhine-Siegen model, it is just a catastrophe. So good enough that most of generators are going to get rid of this model. So finally, some practical message for Monte Carlo generators, as far as I understand what follows from this very interesting workshop. Okay, so first of all, kind of obvious, improvements, should be done are really important. Some of them are more difficult, some of them are not that difficult. So probably spectral function, should be a default option for CCQE. However, as we already discussed, before more rigorous computations are available, which is probably, as far as I know, the scale of half a year or so. So, two-body current contribution, which is large, must be covered with some combination, and we should try to make it in the smallest possible degree inconsistent. And a kind of obvious constraint is to compare to the minimum neutrino and neutrino data as a consistency, experimental consistency check, at least that. And then I have a feeling, these better computations are arriving, but we'll never be fully satisfied, okay? Because first, those computations are non-relativistic, so there is some obvious limitation in terms of neutrino energy, probably. Then, experimentalists need, carbon is great, but then there is a demand for oxygen, argon, iron, etc., etc., and I think it is unthinkable to have them. Then also, this probably can be done, but Monte Carlos need predictions for final state nucleons. Okay, so we need to know, which is the isospin of ejected, knocked out nucleon, and also which is would like to know how transport momentum is distributed into a pair. So perhaps we can get already some information from existing helium-3 and 4 computations, because maybe this information can be somehow picked out. Would be very useful for Monte Carlos. So, okay, so finally, I mean, summary of summaries, correlations are very important, okay? Okay, thank you.
More questions, comments?
Yeah,
So is it fair to say that we're in agreement that multi-nucleon correlation must be included in a viable model now?
yeah, I think so.
And there are different approaches, but
Yeah, I think we should. Yeah, yeah. I mean, they are. I mean, they are. It is a consensus that. I mean, this two-body current contribution is should be there.
not
So
just-
there was.
not just tweaking form factors. We need to
Yeah.
get in the right physics of this correlation.
Yeah, I think so. It is better. I mean, not to make this in a say, provisional way, because then we will pay a price. I mean, experimentals will pay a price. I mean,
Especially if we ever want to get nucleon
yeah.
recoil distributions correct.
Yeah, because I want to keep going in the same direction. On the other hand, if you have spectral function that has correlations in it and you put a two-body current on top of it, you've got a problem.
Yeah.
So we opened a big can of worms here. At least in my mind, you're driving for excellence in one direction, you drive excellence in another direction, and oops, you got a problem.
Yeah, for-
So that was, to me, that was a very, very important bullet. What's the error you get in putting the best one body and two bodies together?
I mean, I think we should keep experts in the room. I mean, and to ask for recommendation how to. I mean, which is the best way to proceed with current. I mean, with current models.
Do we want to wait for one?
Yeah, yeah, sure, yeah.
It's a real important discussion.
I think another criteria should be, we should ask, is there any way to get, what's the best way to get, best possibility to get realistic nucleon recoil
Yeah,
distribution?
yeah,
If we want
yeah.
it. Some approaches may be easier.
Yeah,
than-
yeah. Something. I mean, what.
Even if the others may be better, in the long run.
Yeah, what is currently done is just, is doable, because, we always find. What Bill Donnelly was proposing, he was telling that, in some cases, most of momentum is transferred to only one nucleon, but then it is difficult to get both nucleons on shell, so it is.
I think that's
It is tricky. It's tricky to get kinematics closed.
I think that's the most important information. This moment, neither Genie nor Newt have any realistic, theoretically motivated way to create nucleon. It's just an ad hoc solution. It's a reasonable.
Space.
Yeah, but there is maybe way to distribute
Yeah,
momentum.
if we
some
can do a little
theoretically
bit,
motivated.
a little better would be.
Well, we'll talk about that in detail, but a lot of it's based on data in various ways. It's not ad hoc.
No,
It's-
that's
it's-
data.
Of course, there are FSI effects on the top, so probably many details are smeared out. Okay.
Yeah, the way to
So-
create two nucleons, just center mass and separate two.
Okay, if you mean that, yeah, no.
Because that's
I
the
thought you
only
meant
one.
something else, you were,
Yeah.
it seemed to be all
No,
encompassing.
it's just a message. Because that's the only way to tell this process really.
I thought the proposal Jerry made, Jerry Garvey, it seemed like one way we could go, where you had to have a spectral function that was just the mean field. Well, we should wait till Jerry is here, because Jerry had a one-slide, recipe that I thought
Yeah.
at least had some internal consistency to it. More than just taking the spectral function and adding on two other pieces.
So I sort of plead for the theorist. I think one of the really nice things that came out of this is that, for example, Marco had to make some assumptions about where the enhancements are, but then we come in with a different technique, Green's function Monte Carlo, and we're able to check his assumptions. And if every theoretical approach is going to have a limitation but have certain strengths, and if it can somehow cross-check certain assumptions about the other calculations, and that gives us a lot more confidence. And so if something can be done about the boost factors, if somehow Marco cannot directly approach this issue, but some other framework can demonstrate the impact of that and whether it's under control or not, then that would also be very nice. So that's one of those things where we had to really rely on the theorists to collaborate with each other. Because I I have no idea, you know, the prospects of someone with their model and someone else's with their model, what their prospects they have to cross-check their assumptions.
So on that specific point, I asked Bill what the prospect was for a fully relativistic model and then being able to check the non-rel stuff. And the answer was, please give us a little bit of time, but that's something that they want to do. So I think that that's a realistic thing, and they think it's possible.
He promised yet again that he'd have a fully relativistic measuring exchange curve model within the Fermi gas, and I'm really looking forward to that.
Yeah.
He promised that this summer, and he's still promising it. I talked to the student, he said, well, it's hard. These older guys are promising things, and I'm working hard, but I'm not there.
Experimentalists do that too, you know.
Sure do.
So since we have a couple of theorists in the room who thought about this, I mean, theoretically, what is the most generic thing that you calculate that would be universally calculated and that could be plugged into a generator? Is it the response functions? Is it the components of the hydraulic tensor? Either.
Yeah.
Okay. It's the same. Okay. Okay.
I don't know.
So if we had like an interface in the generator to those, people could do separate calculations and plug the answer to that.
We have already started doing that with the Nieves model.
The hydraulic tensor.
We get the harmonic tensor and then we can compute the weight of the air.
Yeah, because this can be given in the form of tables. So.
I think that's something you've stressed, response functions.
Yeah, because they are, I mean, just tables, 5 tables, and then they are applicable for whatever, both neutrino, anti-neutrino, whatever energy. So this, I mean, once they are produced, it takes half a year or so. Okay, but then they can be used. Yeah.
It takes a few days to do one of these hazards.
Hmm? No, I'm referring to the time scale of those tubular current contribution. I mean these are very complicated. So we must.
Good. Any more questions for Jan or for us?
Yeah, for.
Well, thank you, Jan.
Okay.
Thank you, everyone.
Yeah.